All right, let's jump right in. Today we're talking about the fundamental language of science. This is the system we use to measure, describe, and, understand the entire universe. We're diving into SI quantities and base units.
So let's kick this off with a massive question. How in the world do you measure everything? Think about it. Physics deals with this absolutely mind-boggling range of scales. On one hand, you've got things that pop into existence for just tiny fractions of a second, and on the other, you've got the age of the universe itself. How can one single system possibly handle all of that?
Just look at this. The sheer range here is almost hard to believe. You're looking at lengths of 10 to the minus 15 meters for a nucleus, and then, all the way at the other end, the edge of the known universe is 10 to the power of 26 meters away. Or what about mass? An electron is 10 to the minus 30 kilograms, while the entire Milky Way galaxy is 10 to the power of 42. There's just no way you're going to write out all those zeros every time. It's impossible. This is exactly why we need a powerful, standardized system to make sense of it all.
So, to get a handle on this, here's our game plan for today. First, we're going to look at the universal measuring system that scientists all agreed on. Then, we'll see how pretty much everything is built from just a handful of fundamental units. After that, we'll learn how to use these units as a secret weapon to check our work. And finally, we'll put it all into practice and solve some real physics problems.
Okay, so first up, that universal system. It's officially called the System International, but pretty much everyone just calls it SI. You can think of it as the agreed-upon global language for science. It's what ensures a scientist in Japan can perfectly understand and replicate the work of a scientist in Brazil. It's a huge deal.
Now, at the very heart of this system is something called a physical quantity. And this is super important. It's not just a number. If I just say 7, it means nothing, right? Is that 7 seconds, 7 miles, 7 potatoes? But if I say 7 kilograms, boom, you have real, solid information. A physical quantity always needs both parts. The numerical value, that's the how much, and the unit, which tells you of what.
And these quantities really come in two flavors. On one side, you have your base quantities. These are the absolute fundamentals. They are the building blocks of measurement, kind of like the primary colors. You can't break them down into anything simpler. Everything else, and I mean everything, is a derived quantity. These are made by combining those base quantities, just like you'd mix red and blue to get purple.
And here they are, the magnificent 7. These are the fundamental building blocks of our entire physical universe, the 7 SI base quantities. We've got length in meters, mass in kilograms, time in seconds, and a few others. You're going to want to get real familiar with this table, because every single measurement in physics, no matter how wild or complicated, can be traced right back to a combination of these 7 things.
Okay, so we have our alphabet of 7 base units. Now the fun begins. How do we actually use them to write the entire language of physics? How do we handle those ridiculously huge and tiny numbers we saw earlier? And how do we build new ideas out of these simple blocks? So remember that slide with all the crazy numbers? Writing those out every single time would be a total nightmare. So to make life way easier, we use prefixes. They're just simple shorthands for multiplying or dividing by powers of 10.
And here are the most common ones. You've definitely seen these before. Kilo for 1,000, like in kilogram, or milli for 1,000th. But we go way further in both directions. You've got giga for 1 billion, like in gigabytes, and nano for 1 billionth, like in nanotechnology. Knowing these prefixes is absolutely crucial because they let us talk about these vast scales without our brains melting.
So that's how we handle scale. But what about creating totally new concepts like speed or pressure or force? Well, it all comes back to that idea of derived quantities. Like it says here, they're simply made up of one or more of our base building blocks. Let's see this in action with a super simple one, speed. We all know the formula, right? Speed equals distance divided by time. So to figure out its units, we just swap in the base units. Distance is measured in meters, and time is in seconds. So the unit for speed is meters per second. Easy enough. Now, in physics, you'll often see this written as ms to the power of -1. It's just a cleaner way of writing it. And just like that, we've derived a brand new unit from our base units. Okay, this next part is a real superpower for anyone studying physics. Seriously, this is a game changer. We're going to see how we can use our knowledge of units to check if an equation is even possible before we even think about touching the numbers. The idea is called homogeneity, and it's simple. For an equation to be physically valid, the base units on both sides have to be exactly the same.
Think about it. You can't add 5 seconds to 2 kilograms, right? It's nonsense. It's the same in physics. If the units don't match up, the equation is just plain wrong. Period. It's a fantastic way to catch mistakes.
So, you ready to put it to the test? Here's a classic equation from mechanics. It says that the work done on an object equals its change in energy. But is it homogeneous? Does it actually make sense from a unit's point of view? Let's find out.
Okay, let's get our hands dirty and break down each piece. First up, work done. That's force times distance. The base units for force are kilogram meters per second squared, and distance is just meters. Multiply them together and you get kilogram meters squared per second squared. Got it? Now for kinetic energy. The half is just a number, so we ignore it. Mass is kilograms, and speed squared is meters per second, all squared, which gives us kilogram meters squared per second squared. Hey, that's the same thing. And finally, potential energy. Mass times the acceleration of gravity times height. And what do you know? You get kilogram meters squared per second squared again. They all match. The equation is homogeneous. It holds up.
Oh, and just a quick heads up on something you'll see all the time in science. When you see a table or a graph, the labels on the axis might look a little funny, like time/s. All this means is that they've divided the physical quantity, which is time, by its unit, which is seconds. The reason? It leaves you with just a pure number, which is exactly what you want to plot on a graph or put in a table. It's just a standard convention to keep things neat and tidy.
All right, time to put it all together. We've talked about base units, derived units, prefixes, checking our work. Now, let's see how this all plays out when we're solving some actual problems you might see on a test.
First up, a classic prefix conversion. This is a super common type of question. We need to figure out how many micrograms fit inside 1 single milligram. This is all about knowing your powers of 10.
So the trick here is to use the gram as our common ground, our reference point. We know 1 gram is the same as 1,000 milligrams, or 10 to the 3. We also know that 1 gram is 1,000,000 micrograms, or 10 to the 6. Well, if both of those things are equal to 1 gram, they must be equal to each other. So then we just do a little bit of algebra. We divide 10 to the 6 by 10 to the 3, and we find out that 1 milligram contains 1,000 micrograms.
Now for a totally different kind of skill, estimation. This is sometimes called order of magnitude thinking. This isn't about getting a perfect, precise answer. It's about developing a gut feeling for the world. What's a reasonable number for these everyday things?
And the answers here are all about being in the right ballpark. A standard jar of peanut butter is about 500 grams, right? So 5 times 10 to the 2 grams is a great estimate. An orange? Maybe 300 cubic centimeters? Again, the exact number isn't the point. What's important is knowing it's not 3 grams or 30,000 cubic centimeters. This feel for reasonable numbers is a huge, huge part of being a good scientist.
Okay, let's ramp up the difficulty a little bit. We've got an equation for the drag force on a skydiver, and you can see there's this constant in there, c. The question is asking us to prove that this constant is dimensionless. In other words, that it has no units at all. How on earth do we do that? You guessed it, we use our superpower, homogeneity. Let's look at the left side first. The base units for force are kilogram meters per second squared. Done. Now let's look at the right side, but let's ignore c for a second. We've got density times area times velocity squared. Now, if you carefully multiply all those base units together, you get the exact same thing, kilogram meters per second squared. The units on both sides already match up perfectly. So what does that tell you about c? For the equation to balance, c can't have any units. It has to be just a pure number.
Now, let's switch gears a bit. Instead of a calculation, here's a conceptual question. We've learned the what and the how of SI units, but this one's about the why. Why is this whole system so incredibly important?
It really boils down to 3 big things. First, consistency. It gives everyone a single, standard language to use, whether you're a chemist, a biologist, or an engineer. Second, it allows for clear communication. Results can be shared and understood all over the world without any confusion. And third, it just leads to fewer errors. Can you imagine the chaos if every country used its own system of measurement? The SI system prevents that. So, let's end with a little challenge for you to take away. Look around you, right now. Find an object, your phone, a book, a coffee mug. What's your best guess for its mass in kilograms or its length in centimeters? This ability to see the world around you in terms of its physical quantities, that's the very first step to thinking like a physicist. Give it a try. Thanks for joining me for this explainer.